Hi everyone, and welcome to this talk about how to generate synthetic data in financial time series. Thank you, very heartwarming thank you for your very kind introduction. You actually stole my punching lines just when I was trying to calm my nerves. As it was said, I'm Elena. I've spent about 15 years in the field of AI and data science. I used to work in a bank here in London for approximately 5 to 7 years. Before moving back to Greece, where I have both a business role as well as an academic role. So this today's talk and this work has been part of me being a supervisor of a tremendous team for 4 amazing students. One of them, Stamatis, is here, but we also have Alkiviadis, Konstantinos, and Evangelos, who are also main contributors towards this project. So since I had a financial background and I played with AI in finance, I decided why not make my students suffer and throw deep learning in combination with time series, as well as financial data in the mix to make them hate me. Somehow, though, they still managed to talk to me and they didn't complain at all, and they actually picked up on that challenge. So why the fuss? Why synthetic data, and why is it important? So first and foremost, what are synthetic data? When we're referring to synthetic data, and we know that we live in a Gen AI era where a tremendous amount of synthetic information is accumulated and generated on a day-by-day basis, especially since the booming of the LLMs. But synthetic data can be far more than just textual information and/or images. So in particular, synthetic data are artificially generated data that mimic real-world data. They're most of the times generated by models and algorithms, and we're trying to capture as much of the underlying trends and patterns of our original data. And their significance is such that it's estimated that the future of AI, and we're going to be training our models, and they're going to be based in the majority of the cases on synthetic data as opposed to real data going forward. Why do we need synthetic data? First and foremost, we've seen that, especially with the latest cutting edge and state-of-the-art models, we need a tremendous amount of information in order to train and evaluate the performance of our models. Now, for those of you that have worked in banking or other heavily regulated industries, I personally come from both from bioinformatics as well as finance, to really, really heavily regulated industries. So it's not always the case that you have an abundance of data handed over to you. So data can be limited or absent. Cases of ethical considerations need to be taken into account. Everything you do is screened heavily by a regulator. You have to consider private identifiable information as well as privacy issues. And of course, last but not least, very commonly, the data can be unannotated and unlabeled, which is a very time-consuming, costly task, which involves a human in the loop. So the main focus of our work has been to screen the capabilities of synthetic data. And again, I have to repeat that this piece of work is not for a particular company. It's under a capstone research project. So the main focus of our work was can we preserve some privacy in the data? Can we use it for data augmentation? Can we use it with variations of anomalies in our data and help towards anomaly detection, as well as how can synthetic data help towards algorithmic development? Now, why synthetic data in finance in particular? As I mentioned, and I'm sure I've spoken to quite a few of you in the room, so for those of you that have worked in financial institutions, we know that data are often quite sensitive. They can be siloed. It's very difficult to transfer data from one point to the other, from one database to the other, let alone from one country to the other. You need a million of sign-offs along the way. And it can be also a money-making and proprietary information. Therefore, everything you do has to be critical and it has to comply with privacy regulations. Therefore, by using synthetic data, by leveraging the power of synthetic data, you help by providing anonymized data sets without exposing any sensitive information or proprietary information, and you really help towards boosting innovation and improved services. Of course, it can be the case of talking about financial time series without factoring in risk as a factor. So Synthetic data can be also helped towards testing and stress testing various hypothetical scenarios, especially in cases where you have only a sparse amount of data, and or not even representative amount of data. So can you actually cause hypothetical scenarios to test drive what may have happened upon these hypothetical cases? And this is super crucial for assessing the robustness and the resilience of various financial strategies, and help simulate economic downturns or market crashes in cases like that, and evaluate some risk upon them. Last but not least, yet another use case that has been heavily kind of considered when it comes to generating synthetic data has to do with fraud detection. And we know that fraud is an ever-changing field where fraudsters kind of create new ways of beating the system. So synthetic data can really help create new, diverse, realistic, fraudulent activities that we may try to screen and catch, and we can better anticipate and respond to new fraudulent tactics. Therefore, just to sum it up very quickly, advantages of using synthetic data besides the time, the cost, the efficiency, the diversity, the ethical considerations, creating unbiased and scalable data, they really help towards all these things and help with automated labeling and annotation as well. Some of the data sources now that we have used in particular for this project, and we did promise in our proposal to provide some APIs as well. So for those of you that want to play around hands-on with some data of financial nature, one of the data sources was FRED, the Federal Reserve Economic Data. Alpha Vantage API as well, both cases provide an API where you can pick information both as an interday, like daily, weekly, and so on and so forth. They have a variation of options to play around with. Of course, Yahoo Finance, Quandl, Kaggle wouldn't be left out. And at the American College of Greece, we're quite lucky and privileged because we also have license of Bloomberg. So we have started expanding our experimentation towards real-world data for research purposes. Now, our methodology. Over time, we have experimented with playing around with data augmentation techniques, as well as variational autoencoders, which are some of the go-to techniques when it comes to generating synthetic data. But the results of these analyses weren't as good enough as generative adversarial networks, or GANs. GANs have been quite famous. They're quite popular approaches for generating synthetic data. It shouldn't come as a surprise. They're heavily used. However, it's not always the case that GANs are straight plug-and-play tools that you can fuse into time series datasets and immediately make them work. So the combination of GANs along with our NANs and LSTMs in kind of like new ways that we're going to show afterwards, hopefully may catch some of these problems. But first things first, what are GANs and how do they work? So GANs are unsupervised learning techniques where you have two submodels which are trained simultaneously using a process which is called adversarial training. A typical vanilla GAN consists of two main components to neural networks, usually, but not always, but like based on convolutional neural networks. And in this case, you have the generator and the discriminator. And we're going to cover over the course of this talk what each one stands for and how they work. But I think their names are kind of pretty self-explanatory. Now, both the generator and the discriminator are in a constant battle where they're trying to beat against each other and keep on improving their performance. And as such, they result in the generation of increasingly new realistic synthetic data. Now, the overall training process, and again, there is a very nice graph, a visual aid that you can see how the generator and the discriminator works. But step by step, we start by creating Z by sampling a random noise following a suitable noise distribution, such as a uniform, a Gaussian, binomial, and so on and so forth. Then we feed Z to the generator as a way of producing a synthetic dataset, which is commonly referred to as X-fake or fake sample. Now, we pass both X-fake and X-real to a switch block, which randomly selects one of its inputs, and then it passes it on to the discriminator. As a next step, the discriminator will classify this given sample as real or fake, calculate an error upon that, and then backpropagate the error back to both the generator and the discriminator in order to update their weights. Now, as we said, this is like a very first kind of initial vanilla GAN and how it works. But of course, like as with all the advantages, there are a couple of disadvantages as well to consider. The first one, which is a very common problem, is that GAN-based architectures face something which is called the mode collapse. So during the whole adversarial training, where the generator repeatedly, in the case of the mode collapse, the generator repeatedly generates one specific type of data. So it identifies that it can keep on fooling the discriminator with only one type of data, and therefore it will keep on iterating through the same dataset over and over. In this particular case, the problem can go easily undetected, as the metrics would indicate that the model training is running smoothly. The second main problem is a non-convergence failure. So in this case, both the generator and the discriminator cannot find an equilibrium point during the whole training process, and as such, they're causing their loss functions to fluctuate. Now, as I mentioned, in this case, this is a straight-up vanilla GAN, and Stamatis here is going to come in and present to you the time series GAN version and how that can be applied to time series specifically. So, thank you, Stamatis.
Thank you, Elena. Elena talked about the vanilla GAN. Now things get a little bit more complex, because in order to create generative synthetic data in time series, you have to use multiple deep learning models. A time GAN is a sophisticated model which is designed to generate realistic time series data by combining the strengths of both GAN, generative adversarial networks, and RNNs, recurrent neural networks. The network is trained in a way that leverages both supervised and unsupervised learning to capture the temporal dynamics of the data. So we will cut all the names to explain exactly what we're going to present in the code. So we're talking about time series. As most of you will probably know, time series or sequential data can be defined as any data that has time dependency. To model successfully time series, it means that the model must not only capture the dataset features distributions within each time point, but also it should be able to capture the complex dynamics of those features across time. To generate tabular data is far simpler than generating dataset that should preserve temporal dynamics, and that's how we're going to explain later how we did this. So, what's the difference between discriminative versus generative? The key difference lies in their objective, because discriminative are used for classification tasks, distinguishing between classes of the data, while generative models are used for creating new data points that mimic the original data distribution, to be more precise, the joint probability of X and Y. So it's called adversarial because, as Elena already explained, both generator and discriminator are trained simultaneously in a loop. So the generator improves at its ability to generate realistic data, while the discriminator gets better at identifying which of them are fake or real. Indicating that the generator has, in a point, they are so well trained that the generator has learned to produce highly realistic data, because the discriminator doesn't understand it's 50% whether it's real or fake. And the networks. The main networks are the generator, who generates the synthetic data, the discriminator, which distinguishes between real and synthetic time series data, the encoder, which is used for the time series and embeds input time series into a latent space, and the recurrent recovery network, which reconstructs latent representations of the time series back in time. The optionals that in time series may not be optional, the supervisor, it's to enhance the embedded representations because it's highly volatile for the generator. In our case, we also created an autoencoder detector network, which detects anomalies in the latent space. So the embedder maps the raw time series into the latent space. These steps helps in capturing the temporal dependencies in a lower dimensional space. It's typically RNN or LSTM. We use RNNs. And the process is that given the input time X, the embedder produces the latent representation H. Then the recovery, which both of them create the autoencoder, maps the latent representations back to the original time series data space. This ensures that the latent representation contains sufficient information to reconstruct the original data. The architecture is again RNN or LSTM, but they have to mirror the structure of the embedder because both of them are the autoencoders. So if we use RNN in the first place, we use RNN in the second place also. So given the latent representation H this time, the recovery network outputs the reconstructed time series X down. So it's the new X inside of the latent representation. Now the generator produces synthetic latent representations from a random noise. These latent representations should ideally mimic the distribution of the real latent representation produced by the embedder. So again, we use the RNNs, and it takes random noise as input and outputs the synthetic latent representation H fake. The discriminator differentiates between real latent representations and synthetic ones. It ensures that the generation produces realistic latent representations. So again, using RNN, it takes the H, either real or fake, and the discriminator outputs a probability score. If the probability is more to be a real one, it's a real, or it's a fake one. Now the supervisor, as already mentioned, is a network which helps to capture better the temporal dynamics and to mimic better the distribution effectively. It ensures that the synthetic latent representations have similar temporal properties to the real latent representations. Again, using the RNN, it takes the synthetic latent representation, H fake, that the generator has produced, and it produces supervised latent representations, H supervised. Now let's go to the loss functions, to the outcome. The reconstruction loss ensures that the embedder and the recovery can accurately reconstruct the original time series back, which using the mean square error, we can calculate it. Using again the mean square error for the supervisor loss, we ensure that the supervisor network helps the generator produce latent representations with proper temporal dynamics. Now the adversarial loss uses binary cross entropy. It uses both for the generator and the discriminator to ensure that the generator produces realistic latent representations. And I will explain further why we have to log them. Finally, the overall loss, which is the final loss function, and combines all the individual losses mentioned above. Now, we use logs because GAN as a model, it can be notoriously unstable due to the adversarial nature of the discriminator and the generator. So the log function helps in stabilizing the training process by providing smoother gradients. And also, as already mentioned, we use a binary cross entropy, which it naturally includes a log term, and it has to measure the difference between the predicted probability distribution and the actual distribution. Now, the training steps. First, we train the embedder and the recovery networks together using the reconstruction loss. Then we train the supervisor network using the supervised loss. This, as already mentioned, is optional because if you don't have a supervisor, you just skip this step. Then we train the generator and discriminator networks using the adversarial loss. And finally, we fine-tune all networks together using the overall loss to ensure that all components work harmoniously. Let's get in the hands-on now. We used many libraries from pandas, Python, NumPy, sklearn, but what I want to mention here is that the main library is the TensorFlow we used here. You can use also PyTorch, but the PyTorch takes less time, but it's less effective. So we prefer to use TensorFlow for better results. As for data, we use the Fred, as already Elena mentioned, and we get the WTI and the Brent, which are both crude oils, the stocks of these crude oils. The difference is that the WTI comes from the US, primarily Texas, while the Brent comes from the North Sea. So we took data from 1987 to 2020. We picked these two because they have anomalies. So in our case, we create a time series GAN which detects anomalies, and that's what I'm going to explain further. And they follow similar trends. We searched for some null values. They are not that much. You can use the mean or the median, or skip them if there are only a few. So the main parameters is, first of all, the sequence length, which specifies the length of the time series sequence that the model processes. In the context of time GAN, it determines how many time steps each sequence contains. If you use days, and we have 24 in this example, then 24 days. If it's weeks, 24 weeks, and so on and so forth. Then the number of sequences, which defines the number of variables in each time series sequence. And in our case, we have two variables, as already mentioned, the WTI and the Brent, that's why the two. The batch size, which determines the number of sequences the model processes in one training step, and it represents the number of samples fed into the model at once. Now, the scaling is very important because when all features are on the same scale, the model can learn patterns more effectively without being biased towards features that have larger magnitudes. In our case, there was not such a big difference, but you have always to use scaling. You can even use standard scaler, but from the bibliography and from our tests, the min-max scaler works better in this model. Also, we use the sigmoid function, which outputs values between 0 and 1, and you need scaling to be in this scale. Finally, the rolling window, which is one of the most important parts of this model in order to be able to create time series GANs, it generates overlapping sequences using a rolling window approach. Our goal is to prepare the time series data in a way that preserves temporal dependencies for model training. So, some other parameters are the hidden dim, which defines the number of units, the neurons inside the hidden layer, the number of layers, we use three layers here. You can use 2, 3, or 4, but it's prone to overfitting if you use more, so it depends on the data. Now, the train steps, as you already understand what it is, and the gamma, which is a hyperparameter used in reinforcement learning. And in the context of GAN, it's used for regularization mainly. Now, I already mentioned the MSC and the BSC in the loss functions. That's how we instantiate here. The optimizer we used is the ADAM, which adaptive learning rates are beneficial for training time GAN. And we already explained about the RNNs and the random noise, but you can see how to do it in code. We create the functions, and we create also the optimizers here. The networks that we already explained are all RNN. What is very interesting to see here is the hidden units and output units of its network. As you can see, the recovery output units is same with the number of sequences, the number of variables, because we have to output the same variables. Also, the generator and the supervisor has to have hidden units and output units the same, because it gets the same data. And of course, the discriminator, which has only one output unit, the dense output. Here is the training loop that already explained about the losses earlier. You can see our results every 1,000 steps. And as about the interpretation, about the discriminator loss, it starts high, it gradually decreases, but remains above 1, indicating that the discriminator is learning to differentiate, but there's still room for improvement. The generator losses, indicating that generators varying success in creating realistic data, but the G loss drops to 0, which might suggest a specific aspect it's minimized very early. The embedder loss decreases significantly, showing that it effectively captures temporal structures. And the encoder-decoder loss, which is the loss of that I didn't mention already about the detector, because we created an autoencoder to detect the anomalies. It starts high but drops quickly, indicating a successful reconstruction of the data. By the way, we use the threshold of 0.15 for the anomalies. Here you can see the results with the anomalies. And you can see that it goes good with the upward trend, but it fails at understanding the downward trend here. So the synthetic data is smoother and less volatile, suggesting that while the model captured the overall pattern, it may not fully represent the real data's variability and fluctuations. One proportion to avoid this is to use additional metrics or loss functions that emphasize not only trend matching, but also variability and pattern fidelity. Now, this is the difference without the anomalies. Using the autoencoder, we created synthetic data without the anomalies, and the results are much better because both lines show a decreasing trend, suggesting that synthetic data captures the general pattern of the real data. And the real data has more pronounced fluctuation, while the synthetic is smoother, which indicates that while the synthetic model captures the overall trend, it may not fully capture the short-term volatile present in the real data. Here's the evaluation with PCA in Disney, a one-dimensionality reduction and a non-linear and one linear reduction. As you can see, it appears to follow a similar distribution along the first component in the PCA, but it indicates some divergence in capturing the variability of the real data in the second component. While in the Disney, it has great results. It's a non-linear dimensionality reduction technique, which helps in preserving local structure and visualizing high dimensionality of data. Even we don't have a high dimensionality, it works very good, and the data closely matches the distribution of the synthetic and the real in several clusters, indicating that the time GAN is effective in capturing complex patterns. Some areas show very good overlap between both real and synthetic data, suggesting that the model has successfully learned similar structures. However, there are regions where synthetic data is more concentrated or dispersed compared to the real data. And the final evaluation about the usefulness suggests that while the model learns well on synthetic data, its performance on real data is comparatively worse, indicating some limitation in the synthetic data representativeness. About future work, all you have seen right now is about testing, and we already checked, but it's not ready to present, and we can use Bayesian optimization to find the optimal parameters for the model. And the biggest challenge for us is not to avoid the anomalies, but to create synthetic data on the anomalies and blend them together with the rest to create one model and synthetic data for the whole dataset. Thank you very much for your time, and we'll be happy to answer any questions.